Hi, everyone. My name's Sean. I'm a fourth-year undergraduate at MIT, and I'm going to be talking to you today about reoptimizing the particle decay classifiers for the first level trigger of LHCb Run 3. And before we get started, just a quick thank you to Michael, Thomas, and Daniel for their persistent help this summer. Now, here's a high-level overview of the computational task that we're trying to accomplish. So we want to make high-level triggers that basically tell us what decays are interesting and what decays are not interesting from the Run 3 LHCb data. So we have one-track decays and two-track decays. And then once we have these optimal triggers, we want to incorporate this into the algorithm pipeline for LHCb called Allen. The training data that we have to accomplish this is about 180,000 simulated LHCb events. So that's about 2 million individual decays in total. We have 6 different decay types and then one 2018 min bias file that's meant to contain data that's representative of what we actually record when LHCb is running. And then we can use this last file just for efficient trigger rate calculation. Now, of all the training data that we have, the first thing that we need to do is make sure that it's data that could actually be recorded in real data taking conditions. So we need a high enough momentum and a high enough lifetime for the detector to be able to pick it up. So we cut out all the decay examples that don't meet these thresholds, and that removes about 92% of our training data. So for the classifiers themselves, we're using inputs or analysis variables from this LHCb trigger reoptimization paper that's linked in the slide notes. And you can also see the inputs on the table on the right here. So we have different inputs for the one-track model and the two-track model, but we're looking at things like transverse momentum and a few different kinds of chi-squared variables. And then on the bottom here is just a plot to show you basically what this computational task looks like. So we want to take some parameter space that looks like this and draw some meaningful decision boundaries between the blue dots, which are signal, and the red dots, which are noise. So kind of optimizing efficiency while having a low enough trigger rate to be usable. So these models are all boosted decision tree models, and the Python library that we're using to train these BDT models is called CatBoost. And the reason that we're using CatBoost is that it has most of the basic training options for getting good BDT models. And then also the bigger reason is that it can save classifier weights in this JSON format, which is easily read into the Allen pipeline, which is useful for implementing these models later on. So the first task is to split all of our training data into about 75% training and 25% testing. And then another thing that we noticed early on is that the data is almost completely noise. So it's about 92% noise and only 8% signal. So we need to weight all of our training examples so that we have a more balanced training set. And then finally, the hyperparameters for these boosted decision tree models, things like learning rate, model depth, and model iterations, or the number of decision trees in the model, were optimized by exploring a parameter space. I think it was about 100 different combinations of these 3 parameters for each the one-track and the two-track models. And then before we get into the preliminary results of these, let's just talk about some quick things on how we're counting efficiency and trigger rate. So the classifiers are trained on single decay examples, but they're evaluated on entire events. So an event contains about 10 single decay examples. For each single decay, we get an output, which is basically a vector, gives us the probability of it being signal versus the probability of a decay being noise. So if any decay in an event, so again, an event is about 10 different decays, if any of these decays has a high enough probability of being signal, then the entire event is considered to be triggered on. And then we count efficiency as the correctly triggered on events divided by the total number of events. So we only count something like a true positive if the event has a signal and the classifier triggers on that signal decay within the event. So here's a look at the efficiency that we were working with in kind of mid-June. So these are ROC plots. On the bottom, you'll see the trigger rate in terms of log kilohertz, and on the y-axis, you'll see the signal detection efficiency. So this 1 megahertz trigger rate, just to give some background, the input into these classifiers is 30 megahertz. So any efficiencies at this 1 megahertz line, that's a data reduction of about 1/30, a false positive rate of about 3%. And we're kind of going to use this 1 megahertz line as a benchmark for performance throughout the presentation. So the one-track model was giving us about a 14% efficiency at this line, and the two-track model was giving us about a 41% efficiency. So certainly okay, but we can do quite a bit better than that. So one of the things that we wanted to address early on was this decay type imbalance. And what we mean by that is that the training data set that we were using had a lot of training examples for some decays, but very little decay examples for other types of decays. And we can see how this affects performance in these plots to the right. So this is an ROC plot as a function of the decay type. And one thing to note here is that these D decays, so that's the yellow and this brown line, these D decays are much harder for an algorithm to trigger on than the other decays. So we expect these D decays to have significantly lower performance than the other types of decays. And that's just a physical limit on what a D decay is and how that works physically. But we don't really see that in these ROC plots. So one way to address this decay type imbalance is just to downsample all of our training data so that we have the same number of training events for all of the decay types. But downsampling to 2,500 decay examples, that's a pretty low amount of training data. So instead of doing that, we downsample to that number, so the number of smallest decay type, times some integer, what we call the upsampling degree. And I vary this integer between values of 1 to 10 and pick the optimal one. And that was at an upsampling degree of 7. So we downsampled all of our decay types to 7 times 2,500, essentially. And there's a couple other things that we did on top of that, things like randomly shuffling the training data, and then rescaling the input parameters, namely putting all the chi-squared inputs on a log scale before training. And then doing this and a few other things increase the efficiency by several percentage points each at constant trigger rate. So in early to mid-July, we had classifiers that looked more like this. So we have a one-track efficiency of about 28% at this 1 megahertz line, and a two-track efficiency of about 71% at this 1 megahertz line. And what you'll also notice is that these D decays that I mentioned earlier, these yellow and brown lines, now are showing significantly lower performance, which is what we'd expect, and also seems to show that these classifiers are actually learning something meaningful. And then just to compare this DDT performance with something that we already have in Allen, we were comparing the BDT models to these cut-based classifiers. And the cut-based classifiers are basically just several if statements. You might say, like, if the transverse momentum is high enough and if the chi-squared is also high enough, then we consider this to be a signal event. So comparing the BDT models to these cut-based classifiers, you'll see that the two-track classifier has significant improvement, and the one-track classifier only has a slight improvement at the same trigger rate. This is summarized in this table here. So we get about 15% higher efficiency for the two-track and only about 3% for the one-track. But this small performance boost for the one-track data makes sense because this original cut-based classifier was basically based on another BDT algorithm. So it makes sense that these are about the same. And then once you get into the two-track data, you start to really see an improvement with using boosted decision trees instead of just a cut-based classifier. So once we had these models and we knew that they worked reasonably well, we wanted to write some code to implement this into the Allen pipeline. So late July and early August, for me, were spent writing a lot of C++ code to get these implementations in. So I wrote 2 corresponding new algorithms, one for the one-track BDT and one for the two-track BDT, and then 1 new sequence in Allen that basically incorporates these 2 algorithms into the rest of HLT1. I just recently secured an HLCb computing account, so I'll be able to submit a merge request for this code soon. And just as a small note, although the one-track BDT model doesn't really outperform the cut-based model, I thought that this infrastructure might be useful to incorporate anyway, because it just makes putting in more cat-based classifiers easier now that this code already exists. So after we had these models in Allen, we wanted to take one final look at this 3-track and 4-track data to see if we could make any improvements on that. So I wanted to train 3-track and 4-track BDT models, once again taking inputs from this paper that's linked in the slide notes. And you can see the analysis variables here in the table on the right. So there's quite a few more. And then just to give some context, in run 2 of LHCb, we actually had 3-track and 4-track triggers, but they were only used in the second round of high-level triggering. But because the tracking in run 3 is so much faster, these selections can now be made in HLTV1. So it would be definitely useful to get this all working. So I trained 3-track and 4-track models. I excluded all the D decays from these. One, because there is no D decay with 4 tracks, and 2, because it makes the efficiency significantly better to exclude them. And then once again, in a similar fashion, we optimize the hyperparameters like the learning rate and so on by exploring a parameter space of possible values. And here's one final ROC plot that basically compares all 4 of our boosted decision tree models to one another. So we can see here in blue, this is the 1-track, and then all the way over here in red, this is the 4-track BDT. So as you'd expect, the efficiency kind of increases as you include more and more tracks in your selection. And then also this 4-track has a very significant efficiency even in very low trigger rates, only about 100 kilohertz or even less. So it would be definitely very worthwhile to write the C++ code to get these 4-track and 3-track selections into Allen. So here's one final slide, just giving a summary of everything that I did this summer. So the first thing was to optimize the 1-track and 2-track BDT classifiers for run 3. And then we wanted to implement these 1-track and 2-track models into the Allen pipeline. And then finally, we wanted to prove that we would get even better efficiency if we made 3-track and 4-track BDT classifiers. So the 2 next steps for this project are to submit the merge request for the 1-track and 2-track Allen algorithms. And then also just a longer level goal is to implement these 3-track and 4-track models into Allen as well, once that becomes possible. So thank you for having me this summer, and one final thank you to Tom, Dan, and Michael for helping me out.
Okay, Sean. Any questions for Sean? No? Okay. Thank you, Sean.
Sean, I
nice
just
work.
wanted to say thanks. That looks like some really impressive work. Very nicely done and presented.
Yeah, thank you so much. I appreciate that.
Okay. On to our next presentation. Vesal, are you here?
Hi, yes, I am here.
Okay. Go ahead and share your screen and you can get started.
All right. Okay, you can see my screen?
Yep, you're good.
Awesome, thanks. Hi, everyone. My name is Vesal. I am going to talk to you about our progress in putting graph neural networks for particle tracking in FPGAs using HLS for ML. HLS for ML is a compiler for putting deep learning models onto FPGAs. I'll go more into detail about that in the coming presentation. So just an overview about what I'm going to talk about. I'm going to give an introduction to GNN particle tracking and our motivations for trying to put these GNNs onto FPGAs. And then I'm going to talk about our actual progress in implementing these GNNs onto FPGAs using high-level synthesis tools. But before I go into that, just a little bit about me. I'm a fourth-year undergraduate student studying engineering physics at UC San Diego. I've previously interned in consumer electronics and aerospace industries, but I'm a physics nerd at heart, so I'm doing stuff more in that direction right now. So, big data at the LHC. As you all probably know, proton beams collide at 40 megahertz at the LHC, and that leads to really extreme data rates on the order of hundreds of terabits per second. And that requires what's called triggering, which is essentially filtering events to reduce data rates to manageable levels. And there's also similarly high demands for offline data processing as well. So the L1 trigger takes in what we said was 40 megahertz input frequency and has to cut that down to 100 kilohertz. So decisions have to be made on the order of microseconds, and that leads to latency demands that generally require fast computing with FPGAs. And there's also demand for FPGAs in co-processing at the high-level trigger and for offline computing that would increase, or that would decrease rather, the time to physics analysis. On top of all that, with the high luminosity LHC upgrades, these data rates are going to increase. So there's been a push for accelerated machine learning in the L1 trigger as well as for offline computing. And GNNs in particular, graph neural networks, have been demonstrated effective for particle tracking. So we have explored simplified GNNs for particle tracking to be implemented on FPGAs. And we've determined and are continuing to determine bottlenecks for GNN acceleration and a realistic scale of application on FPGAs. So what is an FPGA? A FPGA is essentially a reprogrammable integrated circuit. So they're composed of configurable logic blocks, which we call resources. You can see listed there a few of the standard resources that come into play: flip-flops, LUTs, DSPs, and DRAM. DSPs are particularly precious for neural networks because they essentially represent all of the matrix multiplies that happen in the neural networks. FPGAs are capable of drastic parallelization, so you can pre-allocate resources for specific tasks, and then you can pipeline the tasks so you're working on different data simultaneously. An initiation interval, as you'll see later, is a parameter that describes the degree of pipelining, so you can control how much you're pipelining those tasks. So this parallelization will lower latency and increase throughput. So how do we program FPGAs? Well, traditionally, people use hardware description languages, but that's a pretty long and arduous task. So there's also, in recent years, dependable high-level synthesis tools, which convert C or C++ code to hardware description. And this, of course, drastically reduces the amount of time spent developing the firmware. There's also higher level tools like OpenCL that target broader applications like co-processing, but our focus is on high-level synthesis. So what is HLS for ML that I mentioned earlier? HLS for ML is an open source tool for building and optimizing deep learning models for FPGA applications specifically. It reads in models that have been trained on your standard deep learning libraries in Python, and then converts it to HLS and uses the Xilinx Vivado HLS software to then take that HLS and prepare it for FPGA applications. HLS for ML also comes with common neural network building blocks already built in. That is to say, common activation functions and stuff like that that are used all over the place. So the bulk of this project is about graph neural networks for particle tracking. So let me tell you what a graph neural network actually is. A GNN is a neural network that operates on graph structured data. And you can see a little abstract example of what graph structured data is in the side here. And so there are nodes with their respective attributes and the edges that connect those nodes, which have their attributes as well. So the process of particle tracking with GNNs can be essentially broken down into these 4 steps. First, you have to pre-process the raw data and convert it or organize it as graphs. And then you apply the actual GNN to those graphs in step 2, what's called segment classification or doublet classification, to figure out which of the edges actually represents segments of tracks. And then you post-process those classified segments to produce larger tracks. And then the tracks that have been produced are then fitted with curves that can be used for actual physics analysis. The focus of our project is on that second step, which is segment classification, for which graph neural networks already exist and have been tested and proven. So the input graphs that we put into our model represents a 1/8 phi slice of a tracking detector with node and edge attributes and receiver and sender lists. We set up for a PT cut of 2 GeV and focused on the innermost layers of the tracking detector, similar to the IRIS-HEP GNN pixel project that's ongoing right now. The nodes in the graph represent hits in the layers, and the edges are the connections between hits on adjacent layers within geometric restrictions, of course. The node features are cylindrical coordinates, and the edge features are the differences of coordinates. And the edges are labeled with a 1 if the 2 hits come from the same track, and 0 if they don't. The segment classification model that we've been running with consists of an encoder, which independently transforms the node and edge features to their latent representations. And this layer is fittingly called graph independent. It's a graph neural network architecture. The core consists of an interaction network, which is another graph neural network architecture that updates edge and node features with message passing using those receiver and senders lists. And then a decoder, which using the same graph independence model as the encoder, transforms the edge features into a classification output. So this model, we operated with 8 latent neurons, and the performance you can see here in these plots. On the right, there's a rock curve with an AUC of 0.98, which is outstanding. So we know our model works for segment classification. And this model, of course, now we implemented in HLS. So the HLS model takes in node features and edge features, as well as the receivers and senders lists, of course, and outputs and edge classification as an array. The graph independent layers are implemented as batched dense matrix multiplications, and the interaction network layer retrieves the receiver and sender indices from those lists and concatenates the appropriate edge and node features and does a row by row dense matrix multiplication, the weights and biases. In HLS, there are tunable parameters that we can do to optimize the the implementation. So there's the fixed point bit precision, which we ran for mostly with 16.6, but this is again configurable in the HLS code. And you can also pipeline the neural network or loops, for loops, and etc., with that initiation interval that I mentioned earlier on the FPGA slide. We ran with setting the initiation interval to a reuse factor times the number of edges or nodes, respectively to which portion of the interaction network we were running. But this is also configurable in the code. And we also have it set up to allow for the streaming of the input data, which is just a parameter you can turn on and off, but it comes in handy for larger graph sizes. In this diagram here, there's a very basic representation of what kind of goes on in the HLS code. So essentially we have the input features and they're streamed row by row. And the matrix multiplications happen for the neural network. Those are pipelined, as you can see here. The latency decreases with pipelining, and the initiation interval is what controls the level of staggering for that pipelining. And then you get a single row output, which then leads to the full output as you stream in all the inputs. So the HLS implementation was verified with C simulation, which you can see the output here on the screen. We've compared that to just the output with a Python evaluation script that just evaluates the segment classifier model. The two match to within about 0.2%. So that is good. It's very hopeful for us. The difference, of course, is caused by the quantization that happens in the HLS side of things. So the resources usage and latency for an FPGA implementation is derived from running synthesis tests with the HLS tools. Here you can see this for a small graph of 28 nodes and 46 edges. So the main handles to reduce the resources, of course, are the bit precision, compression, and the reuse factor for the initiation interval. The device we ran these tests on and compared them to is the Kintex UltraScale 115, and our target clock was 5 nanoseconds. So you can see the latency lies at about 2 microseconds, and the initiation interval, as we set and mentioned earlier, is equal to the number of edges. The DSPs, you can see on the right-hand side in the utilization estimates, is at about 2% of what the KU115 has. You may notice the dominant resource being utilized is the LUT at 129% of what the KU115 has. Of course, synthesis tests drastically overestimate these resource utilizations. So we would expect that in an actual FPGA application, they would actually decrease drastically. So we have some scans here of the DSP utilization, latency, and II versus bit precision. The trick is to find a bit precision that is good for the actual model performance, but also doesn't cause excessive utilization of resources and slow down the program. So we've met our proposed goals of implementing an HLS version of GNNs for particle tracking, and we've thoroughly explored the pipelining and other HLS tools available for optimization of this implementation. So in progress right now is a physics performance benchmarking, which after it's complete, we will submit a pull request to the HLS4ML repo with full unit tests and documentation. And also on the side, we're preparing a conference paper for the NeurIPS 2020 Machine Learning for Physical Sciences workshop. So thank you very much. And thank you to my mentor, Javier Duarte at UCSD, and everyone in the GNN Pixel project group of IRIS-HEP for all their support during this summer.
Thank you, Vesal. Does anybody have any questions?
Not
Maybe
interesting,
I
but
can
it's
ask a
crucial
quick
that
one.
we understand a little bit better what
Is
what
that
our
ROC
shared
that you
plans
showed
cannot do, or
initially,
cannot
I guess it was
do,
back
and
on slide
what their
12 or
priorities
13 or
are.
something, is that good enough for the trigger? Is that the performance that's needed?
So there's, this is, as far as we think, decent. Now, as far as if it's good enough for the trigger, I don't think I can really personally speak to that. But this is representative of what we see with the model on a large scale.
Right.
I hope that answers your question.
It goes, yes, thank you. And the second half of my question, actually, I think you may have just answered in the conclusion slide. So I saw the latency versus precision, and I was hoping to see the ROC versus precision, but I guess that's what you refer to as the physics studies and validation that is ongoing.
Yeah,
okay,
that's
perfect.
Right. So very soon that'll actually be out.
Yeah, yeah, really, really excellent talk and excellent work. Thank you.
Thank you.
David, you had your hand raised?
Yeah, I guess, where's my question? I think it's slide 16, you talked about sort of a graph with 28 nodes and 46 edges. Is that what comes out of the training that Gordon was talking about, on slide 12?
Yeah.
Or is that a sort of simplified version?
Yeah, actually this 28 nodes and 46 edges graph is one of the many graphs that was produced in the 2GeV PT cut data set. So yeah, it's actually realistic.
I'm not sure what you mean by many, one of many.
Oh, so the raw data is, of course, organized into graphs. And this example you see here is just picking out a typical graph from the list of graphs that have been created from the raw data.
I can maybe make a comment here. If you go to if you go to your previous slide on the graph construction.
Yeah, so the 2GeV PT cut generates these graphs at the size that we see. Javier, did you want to add something?
Yeah, no, I think you answered it. Just that, so the choices made on this slide impact the size of the graph. So PT of 2GeV cut reduces the size of the graph, splitting the detector into 8 phi slices and 2 eta slices also reduces the size of the graph. So you have multiple of these graphs that are variable size per event.
Yeah, that's exactly right.
Okay, thanks. I'll catch up.
Sure.
Okay, any other questions? No? Thank you, Vesal. That was an interesting talk. Nice work.
Thank you. Thank you.
Next up is Suhaib. Suhaib, are you here?
Yeah.
Okay. You want to go ahead and share your screen?
Yep. Okay, so yeah, good morning. My name is Suhaib, and I worked on the proactive site monitoring.
Sorry,
Oh, sorry.
wrong button.
Oh, all right, here we go. Okay, so yeah, I'll just go through a brief outline of the presentation real quick. So I'll just give like a little introduction about me, the motivation of this project, outlier detection, the attributes we're looking at for the outliers, emailing our data, the limitations, and then lastly, acknowledgements. So just a quick introduction. I am currently a fourth-year undergraduate computer science student at the University of Nebraska-Lincoln. My interest in this topic when Derek presented it to me was I took an introductory course in deep learning last year, and this just was kind of another field into that, and so it was interesting to me. And some of my hobbies, like outside of school and work, are I enjoy skateboarding, soccer, running, driving around late at night and listening to music and traveling. And this picture was like me combining some of those. I got to go to a Manchester United game right before the pandemic hit, so the last bit of fun I had. So the motivation behind this is researchers heavily rely on the stability of OSG sites, and the accounting data is currently stored on the Elasticsearch database. And so we can monitor this accounting data to determine if a site has completely failed, meaning that it's not working and it's like not able to run any jobs. But there's no way to determine a partially failed site. And so the partially failed sites are going to be defined as like sites that are not shut down, but they're not functioning as they should be. We're seeing some discrepancies in the work being done there. So we want to develop a way to monitor and detect these partially failed sites. And we want to send this information to a system administrator to have them look at it more closely. This would allow for them to determine if it's important for them to look at the site or not, and kind of get a better feel for it. And it would allow for a better use of resources and faster job completion. And so you can see in the picture down below, during the last month, HCC has gotten quite a lot of hits and a lot of data to sift through. So I'll get into like how we're going to process and view the trends through all this data. So we're going to first start off with defining what an outlier is. So an outlier is just going to be an observation that appears far away and diverges from an overall pattern in a sample. And for the accounting data, we're going to look at an outlier that is going to be an unexpected. We're going to see that an outlier is going to be an unexpected change in behavior. And so what that means is how we're going to detect these outliers is we're going to look at the last year of usage and determine if the last few weeks are an outlier. And so we have a training data set, and we split it into a training and testing set. Our training is going to be the last year, and we're going to test over the last 3 weeks. And the algorithm that we're using for this is the isolation forest algorithm. This algorithm basically makes a decision tree, as you can see on the picture to the right. And it takes all of your values and basically randomly splits it from the min and the max, and tries to isolate out values. And the closer that those values are to the root node, it determines those to be outliers because they're easily isolated. And the ones that are further down, it says that those are probably not outliers because it took a long time to get those values to be isolated. And so some of the benefits to isolation forest is just that it's heavily scalable. We can use it for a lot of data, and as you saw in the pictures before, we're getting like 50 million hits in a month. So it's easy to, isolation forest works really quickly through all of that, and it does fast detection with low memory usage. So you don't have to use a lot of resources to get this to work. So some of the attributes that we're looking at is currently we're only looking at changes in core hours per VO per site. Some future work that could be added to this is that we could look at changes in CPU time. This could indicate changes in IO patterns. We could also look at changes in user behavior. So something that we could also be looking at is like, was someone submitting a lot of jobs and then they suddenly stopped submitting jobs, or did they suddenly start submitting jobs that they weren't previously doing, or did, on average, are their jobs taking longer to run or shorter? But these are all future additions that we could look into. So these are the graphs that our program currently outputs. It shows all of the VO sites and their usage for weekly core hours over the last year. And these blue bars indicate outliers. So you can see like in CE Crane 1, we have like a large spike in September, and then in OSG Temp, we have a little dip. And so this is how we'll be examining the data. We are interested in these spikes and dips because we want to know what's causing them and why it's happening. So as we can see here, we have usage that starts in April, and we have a large spike in September. And this is something that we'd want someone to look at to make sure that the site is running the way it's intended to be. And so for OSG Temp, we see, this is Arizona State, we see a dip in early September. And we figured that this is because there was a new compute entry point added on August 18th. And so there was an old cluster and a new cluster working simultaneously, but the new CE broke. And so what happened was it was running on two separate ones. And if you look at the graphs from both of those clusters and combine them together, this blue line would eventually come up and meet the orange line, and it would look as normal usage. But because one of them broke, it detected it to be an outlier. And so currently CE operators are looking into this. And we have some emails that are also going to be automated and sent out at the beginning of every week. This will be showing the data from the previous week. These emails will contain a PNG attachment of graphs. And the emails will contain all the VO names that are going to be listed. So you can see in this picture, like all these VOs will show up in the email, and you'll have a little outliers.png file that you can look at to see the graphs. And those graphs are just from a few slides ago. And so we've deployed all this using a Docker container to make sure that it's like running efficiently and it can keep running without having to install any dependencies or anything. And so there's also still some limitations of this project. Currently, there's, as you can see in this Purdue Halstead graph, there are these spikes in usage before, like in previous months. But what our program is doing is it's only determining the last it's only testing over the last 3 weeks. And so only the last 3 weeks can be determined to be an outlier. And they're really the only problems that we can fix too. So if we see spikes months ago, it's not really something that we can fix anymore at this point. And so it's not really important for us to know that that spike happened or for it to detect that as an outlier. But there are also a lot of false positives that can occur. So if someone, for example, has their jobs are just on average taking longer to do now, just because it's the nature of their work has changed. Our program will detect that to be an outlier, but when it gets emailed out to the system administrator and they take a look at it and they determine that the jobs are running fine, this could be a false positive, or just that, like, as we said, if their jobs just are on average taking longer or shorter to run. And so some acknowledgements that I'd like to make is a big shout out and thank you to Derek. Learned a lot through this project with him, and he helped me navigate a lot of the confusion that I had. Carrie Brown also helped a lot with giving feedback on the project and how it was doing. And Tim Cartwright Derek and I had presented this to the factory ops OSG team a few weeks ago, and they gave us a lot of valuable feedback that was important for user focusing and like how these sites are being used and what information we should be getting out of them, and how to like analyze that information and data. And so, yeah, thank you.
Thank you, Suhaib. Any questions for Suhaib?
I just wanted to say thanks. This looks really useful. I'd never heard of the isolation forest before. Does that go through some sort of rebalancing as you build it? Because I usually think of when you build one of these, you know, a forest like a decision tree or something like that. The order and how the tree gets built can depend upon the order the training data shows up as input.
Yeah, so I'm not really sure how the order matters in this, but like it'll randomly split the set in any way, and it just basically looks for patterns. So if like when it trains and looks at the testing set, it's just looking for patterns between the two and trying to isolate those nodes.
Okay, so there's some sort of distance metric at play here, and that so okay, so you said tree, and I think maybe I was thinking of it as like one of these decision trees, and actually it's a more sophisticated animal. All right, perfect. Thank you.
Mm-hmm.
Okay, anyone else? No? All right. Thank you, Suhaib. Nice work.
Thank you.
Up next, our last one, Pratik, are you here?
Yep, I'm here. I'll share my screen now.
All right.
Okay, can you see my screen?
Yep, you're good to go.
Okay, perfect. So, hi, I'll be talking about my summer project on anomaly detection using VAEs and normalizing flows. So let me start with a quick introduction. I'm Pratik. I'm a master's student at WPI pursuing robotics and AI. I received the Diana HEP Fellowship for the summer, and my supervisor was Dr. Maurizio Pierini at CERN. I also previously worked as a short-term intern with the GEM lab, and the GE11 detectors that my team tested have recently been installed in the LHC, so that's something cool. Let me skip straight into my project now. So the objective of my project was to come up with anomaly detection algorithms that aid in new physics searches. So essentially, we are concerned with detecting BSM or beyond standard model events as anomalies. And we chose to explore deep learning based algorithms. Now, my work was part of a larger collaboration with researchers from the CMS and the Atlas experiments. And we also had other people who worked on density estimators and non-deep learning based algorithms, essentially. So the scope of my project is constrained to the use of VAEs or variational autoencoders as potential anomaly detectors. We also went into looking into how we could improve the performance of VAEs using by looking at the latent distributions and how we could improve performance by manipulating that. So I will not go deep into how VAEs work, so due to time constraints, but in general, VAEs have an encoder and decoder setup. We use neural networks to approximate a posterior for the latent variables, which is, and the network also calculates a model likelihood. So essentially, we try to get a latent distribution using the encoder, which accepts the input and outputs parameters to the latent distribution. The latent distribution in general is formulated as a Gaussian, from which we sample the latent variables, which are then passed into the decoder, and we have an output. So in general, VAEs are used as generative algorithms. So essentially the idea is to reconstruct the input using a constrained distribution or a low dimensional distribution, which is the latent space. In our case, we're trying to use these VAEs as anomaly detectors. So the idea here is to train the VAE to reconstruct one class, a single class of events, in our case, the SM standard model events. So with the anomaly, with the VAE trained to reconstruct background or SM events pretty well, when we feed a anomaly or anything that does not correspond to an SM event, the reconstruction is ideally going to be quite poor. So going with a thresholding strategy on the reconstruction loss should help us detect anomalies, which potentially could be BSM events, or the better way to put it would be any event that has a loss or a reconstruction loss higher than the set threshold is not an SM event, and it could be probed further to see if it corresponds to any known BSM events. In our case, we use convolutional layers in the encoder and the decoder, and hence the name conVAE. We also do not use the general elbow loss formulation, which is commonly used in the deep learning community, but we are using a custom sparse loss, which, this work will be documented in a paper which should come out soon, which will also include a work from the other collaborators on algorithms such as KDEs, kernel density estimators, and so on. So you could find information on that. The idea of thresholding on reconstruction loss requires that our VAE is able to reconstruct SM events quite well, and which would in turn mean that BSM events are not reconstructed well. So essentially, we're trying to have a separation on the loss values themselves. So for that to happen, we need to see if we can better reconstruct the SM events, for which we look into the latent space. So the latent distribution being approximated as a Gaussian may not be the best approximation for every case. In general, in the deep learning community, for most tasks, approximating the latent distribution as a Gaussian has worked pretty well. But as I said, it may not be the best distribution for our case, which is why we looked into the concept of normalizing flows. So essentially, normalizing flows are invertible transformations, simply put. So any transformation that takes our input distribution to a target distribution while being invertible at all times is classified as a normalizing flow. So how we use it here is we are trying to find a better distribution for the latent space as opposed to the Gaussian. So we input our latent distribution through a flow model, which is then going to calculate a better distribution, which in turn helps in better reconstruction. So the issue here is we essentially do not know a target distribution that would be best suited for this task. So we intend to learn a suitable target distribution or a better target distribution as part of a single training process. So as the network learns to reconstruct the input, it also learns a better distribution for the latent space. And that is the reason behind why certain invertible transformations are applied when it comes to normalizing flows. So as I mentioned, any transformation could be applied here that is invertible. However, the formulations are in such a way that they are compatible with the training process of a general deep learning algorithm. So the formulation you see on the right here is, I'd say, one of the most basic, or one of the first implementations of normalizing flows when it comes to variational inferencing, and this is called the planar flows, where we have flow parameters u, w, and b, which are taking the input z to a final distribution. So how we calculate the flow parameters is we maintain a parallel hypernetwork, which essentially contains, which could potentially contain a dense network of a single layer or multiple layers as required. And these keep track of the flow parameters that we require. And since this is a single training process, there is no need for external regularizations on the loss. The same loss function that we use to reconstruct is suitable enough. But as I've mentioned in my future work, there could be some exploration in that direction to see if a modification on the loss function will help us learn a better distribution or learn the latent distribution faster. So as part of my summer project, I built and tested these 7 implementations, which I will just quickly go over. So as I talked about, the first formulation I talked about are called planar flows. Here we have Sylvester normalizing flows, or SNFs. So as you can see, the formulation is rather similar. We have flow parameters A and B, and the difference here is that we use the Sylvester's determinant identity in determinant calculations, which has a twofold advantage. So the first one being that the constraints on the flow parameters A and B for the transformation to remain invertible are slightly relaxed as compared to the planar flow formulation. And the computational intensiveness reduces by using the Sylvester's determinant identity. And there are a bunch of simplifications as a result of this in the transformation process itself. So I have 3 types of SNFs implemented, the orthogonal, householder, and triangular SNFs. So those essentially deal with how the flow parameters A and B are initialized. So in case of orthogonal, A and B would be orthogonal matrices, or triangular would be triangular, and householder would be matrices generated from householder reflections. Details of it can be found in the paper linked here. And here in the image, you see a better representation of the hypernetwork that is maintained. So we extract a context H from our encoder, which is then inputted into the parallel network, which then calculates the flow parameters. And essentially we get our transformed distribution, and we sample latent variables from the final distribution, which are then passed into the decoder. So the next formulation would be autoregressive transformations. So autoregressive transformations are invertible transformations. So they do classify as normalizing flows. However, sampling from such formulations is rather complex or cumbersome and requires multiple sequential steps. When we consider the inverse of this formulation, however, the sampling is rather simplified, which is why the name inverse autoregressive flows. So the biggest advantage here is that the flow parameters are rather independent of the input X, and the context H is passed parallelly along with flow parameters that are learned. As a result of this, the biggest disadvantage of this formulation is that we have a very large number of parameters to maintain, and it's just computational. It's the time complexity of each step just increases significantly in order to deal with the larger number of parameters. The final implementation I have is called the convolutional flow, which is rather similar to planar flows, except for the fact that we make use of 1D convolutions as part of the transformation. The biggest advantage of this formulation is that convolutional layers of the encoder and the decoder can potentially be used to calculate the flow parameters as well, and we don't need to maintain a parallel hypernetwork. Another advantage is that, as you must be aware, convolutional layers need to maintain lesser parameters as opposed to dense layers. So we're dealing with a lesser number of parameters, which helps the training process. And also convolutional layers are pretty well suited for a deep learning setup. So the optimizers that we currently use as part of the deep learning community are quite adept when it comes to dealing with the weights of convolutional layers and so on. So the future work here could involve looking at good thresholding strategies. Currently, we've noticed significant separation. So a simple fixed threshold could work for the moment, but it is interesting to look at more efficient thresholding strategies. We also plan to explore on more efficient neural networks for the encoder and the decoders, as opposed to convolutional layers, because in certain cases, the inputs could be sparse, in which case convolutional layers wouldn't be the best way to go. Also, maybe, as I mentioned, we could also look into regularizations on the loss function, which could help learn the flow parameters faster, and also look into inference time optimization. Unfortunately, I don't have a well-collated set of results to present. So we, over this summer, we came up with results from over 120 different model types. So we are still figuring out how to collate them and put them in a presentable manner. So details of that should be in the paper that should come out soon. Also, details of the data set or inputs, if anyone is interested, will be on the paper, but I could share details of the data set if anyone is particularly interested in that. Yeah, so that's an overview of my work, and any questions?
Anyone have any questions for Pratik? No? Okay. Good work. Thank you.
Yep.
Thank you all the fellows who presented today, and thank you to all the mentors for helping them and guiding them. We have another set of presentations next Monday, so hopefully see you all then. So thanks again. Bye.